Hi guys, hopefully you had a great break and your vacation was not too eventful. Oh, there's Mr. Hazelton trying to catch dinner for Thanksgiving. Today we're going to talk about vectors in coordinate geometry. So we'll start with vectors between 2 points. Most of the vectors we've talked about, or all of the vectors we've talked about, have been centered at the origin. And this time I want to talk about vectors between 2 points. We'll start with, let me get my pencil ready. Totally unprepared. Okay. Let's start by making an origin here. And let's draw a vector from 0, 0 to 2, 2. So point A is 0, 0, and point B is 2, 2. If I look at that, there are 2 units to the right. That's my x component. And then there are 2 units in a positive direction for my y component. Okay, so I could represent this vector as 2, 2. All right, let's look at vector from point A to point B. I'm going to draw in my axis again. Ugh, that's really bad. Is there a straight line tool on here somewhere? Maybe not. All right, that's why we have rulers. All right, so point A this time is going to be 1, 1. And point B is going to be 3, 3. All right. So that means that point A is here, point B is over 3 and up 3, so that is here. So if I draw a vector, let's call this vector A to B. All right, if I look and I wanted to look at and put that in component form, I would go 2 to the right and 2 up. Hey, look, it's the same as this vector. And if you look at it, it's going in the same direction and it has the same length. Same x component, same y component. Also, if I have a third vector A to B, and point A is -5, -3, and B is -3, -1. Let's draw that vector. Okay. So point A starts at -5, that's all the way over here, and -3. So it starts here, and then it ends at point B, so that's -3, -1. And I draw that in. Okay, if I want to find the x component, I go 2 to the right. The y component is up 2, and you'll see that the x and y components are 2 and 2, just like my other 2 vectors. So all 3 of these vectors are equal to each other. And you can look at them and see that they are all equal too. Okay, I know that's not going to be enough for some of you. Some of you are going to want a formula to put your vector in component form. So for vector A to B, you'll see that for component form, it's xb minus the x component of A over the y component of B minus the y component of A. For instance, if we take our third vector over here and we want to put this in component form, the x component of B is -3, and then we're going to subtract negative 5, the x component of point A, and then for the y component of B, that's negative 1, we're going to subtract the y component of point A, which is negative 3, which ends up being negative 3 plus 5, which is 2, and negative 1 plus 3, which is also 2. So that's the formula for, this is the formula for finding the vector in component form. The most confusing thing about it is that you have to remember that the second point comes first and you subtract the first point from the second point. Another way to look at it is if I'm at negative 5 and I want to get to negative 3, how far and in what direction do I move? Well, from negative 5, I move 2 to the right, and then if I think about the y component, I'm at negative 3 here, and I want to get to negative 1, that is up 2. So that's another way to look at it if you're not a formula person. Avery, I might be talking to you. So, as a, whoops, drop the pencil. As a recap, if I want to put a vector in component form from A to B, it is x of my second point minus the x component of my first point over the y component of my second point minus the y component of my first point. And you'll notice that if I have, if my first point is at the origin, then the second point is just wherever the x and y steps are. So on the previous page, when I had a vector 2, 2, all three of those vectors, if it's at 0, the second point just ends where the components are. And something else you can do is find the distance between 2 points. So that's also known as the magnitude. Oops, I need the pencil, not the laser. AKA magnitude. Also written as magnitude or sometimes magnitude. If we take our vector that went from point A being negative 5, comma, negative 3, and B was negative 3, comma, negative 1. If we wanted to find the distance between these 2 points or the magnitude, we would just use the formula for distance, which is xb minus xa squared plus yb minus ya squared. It looks like the distance formula from geometry, where instead of b you had x2 minus x1 and y2 minus y1, same formula. Just that we're going from point A to B. So the distance in this case would be negative 3 minus, or plus 5, because it's minus a minus, squared, plus negative 1 plus 3 squared, which ends up being 2 squared plus 2 squared, which would be radical 8. It's as simple as that. Okay, first example. We have P as 1, negative 2, and Q as 3, 1. First thing we want to do is find the vector PQ and the distance between points P and Q. So to find the vector PQ, I want to find the components. So that's going to be the x component of Q minus the x component of p, and then the y component of q minus the y component of p turns to addition, and I get the vector okay. Let's check your answer. If first we're going to find vector AB, and to do that we're going to subtract the x components with b being first, so -1 minus 2, over the y components, -2 minus 7, which gives me -3 over -9. So that's my vector A to B. If I were to draw that from the origin, I'd have to go over left 3 and then down 9 somewhere, and that would be my vector. Well, probably not that exactly. And remember that I can also write this vector as -3, -9. These mean the same thing. Okay, and now if I want to find the distance is the square root of -3 squared plus -9 squared. Well, that square should be on the outside. And that ends up being -3 squared would be +9 plus 81, which would be the square root of 90. Great. Now let's see what else we can do with vectors. Let's see. We have a line here. Find the coordinates C and D. So all of these segments are equal. That's what these little marks mean. So the segment from A to B equals the segment from B to C, which is equal to the segment from C to D. So let's figure out what A to B is first. So vector AB would be -1 plus 2, and then -2 plus 5. So that vector is -1 plus 2 is 1, -2 plus 5 is 3, so that's my vector, 1, 3. That means that the distance between this point here and this point here must also be 1 and 3. So point C would equal point B plus vector AB. So that's going to be, point B is -1, -2, plus the vector would be 1 and 3. That gives me 0 and 1 for point C. So C is equal to 0, 1. Those are the coordinates of C. All right, so for point D, let me erase some of this stuff. I'll leave it up. All right, so point D is going to equal point C here plus this vector A to B again. So if C is 0, 1, and we add the vector A to B to that, we end up with 1, 4. So point D is 1, 4. You'll notice that these here are not vectors, they're just points on the line. Okay, here's one for you to try. I want you to find the coordinates of C to D on this line. of these segments are equally spaced, and use the same method I used in the last video, or in the last slide. Stop this when you're ready to start and restart it when you're ready to check your answer. All right, let's first start by finding vector A to B. So it's going to be 2, 3, plus 1, minus 5. Right? 2 minus negative 1 would be plus 1, 3 minus 5 would be the y component, which gives me components of 3, negative 2. Okay? So coordinate C is going to be B plus this vector A to B. That's going to give me the coordinates for C. So B plus vector A to B. So B is 2, 3, and if I add my components, I end up with 5, whoops, not divided by 1. So coordinates of C is going to be 5, 1. All right, and then D is point C plus that vector A to B, because it's the same distance. So since C is 5, 1, and I add vector A to B to that, I get 8, negative 1. So those are the points for D. Okay, the last thing we're going to do is use vectors to show that ABCD is a parallelogram. So I want to prove that ABCD is a parallelogram using vectors. So if I look at the vector A to B, well, that's going to be 3, 1, minus, or plus 2 because it's negative 2, minus 5. And I end up with the vector 5, negative 4. If I look at vector D to C, then it's 2, negative 1, plus 3 because it's negative 3 here, and minus 3, which gives me the vector 5, negative 4. So I have two equal vectors. That means that side A to B and D to C are parallel to each other because they have both the same x step and y step. So they're parallel, and they also have the same distance. So they're the same length. Wow, I bet you wish you learned about vectors when you were taking geometry. Okay, here's one for you to try. I want you to use vectors to find the remaining vertex of this parallelogram ABCD. You're going to look for the coordinates of D. So pause this, figure out what they are, and come back in a few minutes and check your answer. Okay, so I'm going to use the vector A to B, and I find that vector A to B is 2 plus 1 over 4 minus 3, which is a vector 3, 1. All right, and then I need to find vector D to C, and that way I can find the vertex. So vector D to C is going to be negative 2 minus the x coordinate of D, and negative 1 minus the y coordinate of D, And that has to equal the same thing as vector A to B for these to be a parallelogram. So that has to equal 3, 1. Okay, so I have to say to myself, negative 2 minus what is equal to 3. So I would add 2 to both sides, and I would get 5. So negative dx is 5, so dx would be negative 5. And then negative 1 minus the y-coordinate of d has to equal 1. And then when I add 1 to both sides, negative dy would be equal to 2. So the y component of that would be negative 2. So the coordinates of my vertex, D, are negative 5, negative 2. That's it for today.